Okay, students. Now we'll see the M array signaling. Okay, before we start the M array signaling, for better understanding of this, I want to explain one important one. QCM, quadrature carrier multiplexing. Quadrature. First, if you studied this, then you can easily understand the M array signaling. Quadrature carrier multiplexing. Okay, this is the quadrature carrier multiplexing. What is quadrature carrier multiplexing? See, in analog communication, we studied frequency division multiplexing, FDM. What is frequency division multiplexing? Transmission of more than one signal through a single channel is called as multiplexing. But if this multiplexing is based on frequency, for transmission of message 1, I required a carrier frequency of FC1. For transmission of message 2, I required a carrier frequency of FC3. For transmission of message 3, I required a carrier frequency of F. For different carrier frequencies, the message signals are to be transmitted. Then this is called as frequency division multiplexing. On our starting analog communication classes, right? So now what is my intention? For one message signal, I want to generate one carrier at the transmitter side, receiver side, local oscillator, all these things. Instead of this, I can have another idea. Now two message signals. Here actually in a old fashion, n number of signals, n number of carrier frequencies. But here, two message signals, but I am using only one carrier frequency. I just use only one carrier frequency for the two message signal transmission. If it is possible, then it is an advantage or not? Yes, then you can successfully utilize a single carrier for transmission of two signals without interfere, then that is the greatest advantage. Okay, so that we are doing here. So this is the message signal 1, M1 of t. Now this is the product modulator or balanced modulator or product multiplier, all are same. So now this is the carrier cos 2 pi fct. Now what is output here? M1 of t into cos 2 pi fct, modulated signal. Now this is the second message signal, M2 of t. So we required another carrier, but what I am doing here is this carrier, if I undergoes a phase shift of 90 degrees phase shifter. Now this is cos 2 pi fct. Now this is sin 2 pi fct. Now the second message signal with the same carrier, but these two carriers will not interfere with, these two message signals will not interfere each other because these two carriers are quadrature in phase. So this is M2 of t into sin 2 pi fct. Now these are the two signals which are multiplexed with the same carrier frequency. Now it is transmitting through a single channel. Now this is the modulated signal, multiplexed signal. We call it as a multiplexed signal. Now at the receiver, now again same product modulator or balanced modulator, all are same. Now I use a local oscillator here. The local oscillator is used to generate the carrier frequency which is used at the transmitting side. Now this is same, the carrier frequency which is undergoes a phase shift of 90 degrees. 90 degrees phase shifted. Now this is the product modulator. Now we'll see, we'll check. Now this is the quadrature carrier multiplexed signal here. Now what happened here? The output of the balanced modulator 1, this is balanced modulator 1, this is balanced modulator 2 at the receiver side. This is the balanced modulator 1, balanced modulator 2 at the transmitter side, and this is at the receiver side. Now you just see here, output of balanced modulator 1 at the receiver side is S of t, modulated signal S of t multiplied with cos 2 pi fct, which is nothing but m1 of t into cos 2 pi fct plus m2 of t into sin 2 pi fct multiplied with the local oscillator generated signal, which is cos 2 pi fct. Is that right or not? So now if you see here, if you multiplied, what happened? Cos into cos, cos square theta, therefore m1 of t by 2, m1 of t by 2 into cos 2 pi into 2fc into t plus, if I multiply with 2, m2 of t by 2, 2 sin theta cos theta sin 2 theta, sin 2 pi into 2fc into t. Now at the receiver we are expecting a low frequency information, therefore this is the low pass filter. Now this low pass filter will not eliminate, will not allow this high frequency signals. Now this is m1 of t by 2, then this scaling factors you can easily eliminate. Now in the same manner, now output of balanced modulator 2 at the receiver side, which is nothing but S of t multiplied with sin 2 pi fct, which is nothing but m1 of t into cos 2 pi fct plus m2 of t into sin 2 pi fct into sin 2 pi fct. Now which is nothing but m1 of t by 2, 2 sin theta cos theta sin 2 theta sin 2 pi into 2fc into t plus m2 of t sin square theta is 1 minus cos 2 theta by 2, cos 2 pi into 2fc into t. Then this is not allowed by our low pass filter. Now this is the low pass filter here. Now this low pass filter output, which is nothing but m2 of t by 2. Clear or not? So now see here, you can get back the original message information at the receiver side successfully, but here two message signals, are transmitted with a single carrier frequency, but these two signals which will not interfere because these carriers are orthogonal to each other. Therefore, this is called as quadrature carrier multiplexing. Carriers are quadrature in phase and this is multiplexing. Therefore, due to this orthogonality nature, due to the orthogonality between the carriers, there is no interference. Therefore, it is also called as orthogonal frequency division multiplexing, OFDM. Orthogonal frequency division multiplexing. Orthogonal frequency division multiplexing. OFDM. Okay. Due to the orthogonality between the carriers, there is no interference. Therefore, this quadrature carrier multiplexing is also called as orthogonal frequency division multiplexing. And one more thing, due to this orthogonality behavior between the carriers, even there is a phase mismatch, there is no quadrature null effect. When phase is 0, this signal is coming. When phase is 90, this signal is coming. Now, the phase is 0 to 90 degrees, output will not 0. Therefore, due to orthogonality between the carriers, there is no quadrature null effect. Okay, note down. Okay. Now see students, now earlier we just completed binary signaling. Binary means either bit 1 or bit 0, only binary 1 and binary 0. For transmission of binary 1 and binary 0 for the longer distance or transmission of bits 1s and 0s through a digital communication system, we need to take the help of the carrier, and that modulation techniques are called as amplitude shift keying, frequency shift keying and phase shift keying. ASK, FSK, PSK. But these are the transmission of bits 1s and 0s. Therefore, this is called as binary ASK, binary FSK, binary PSK. Now, what is binary PSK? Transmission of binary 1 and binary 0. So, therefore, this is only 2, 1 and 2. Therefore, this is 2. Therefore, this is called as 2 array PSK, or we may call it as 2 array FSK, or you may call it as this is 2 array ASK. What is the meaning of this? 2 array means transmission of 2 discrete voltage levels, transmission of 2 discrete voltage levels, because this is 2 array. 2 array means transmission of 2 discrete voltage levels through a digital communication system. So we'll take the help of the carrier and a modulation technique. Therefore, this is called as binary signaling, or we may call it as 2 array signaling. Okay, this is called as binary signaling, or we may call it as this is totally 2 array signaling. Or there is another names. This is also called as coherent ASK, or this is called as coherent FSK, or this is called as coherent PSK. Okay, these are the names for this, because the transmission of 2 discrete voltage levels, transmission of 2 binary 1 and binary 0, 2 discrete voltage levels into a digital communication system. But out of this, you are finally selected VPSK or 2 array PSK or coherent PSK, because here bandwidth and probability of errors are less. Okay, but the common problem of all these things are coherence, synchronization, quadrature null effect. This is a problem here. That's why a slight modification of PSK, which is nothing but DPSK. Now we also call as non-coherent PSK is called as DPSK. Non-coherent PSK is called as DPSK. Now this is the finally we are using without error on all these things. So what I am saying is, this is the whatever the binary signaling what we completed earlier, but now this is M array signaling. Now here you are just transmitting of a 2 discrete voltage levels, but what is the meaning of M? M is nothing but transmission of M discrete voltage levels into a digital communication system, or transmitting of M symbols or nothing but M discrete voltage levels into a, or transmission of M discrete voltage levels or M symbols into a digital communication system is called as M array signaling. Transmission of 2 discrete voltage levels through a free space by digital communication. Now similarly, transmission of M discrete voltage levels or transmission of M symbols through free space by digital communication system is called as M array signaling. Okay, is called as M array signaling. Okay, so the transmission of M discrete voltage levels, I want to transmit M discrete voltage levels through a free space. Then you ask one question, sir, one discrete voltage level, one carrier. Now similarly, M discrete voltage levels, M carrier means again it is frequency division multiplexing. Now your complexity and cost and everything will be increases. So now I want to transmit M symbols or M discrete voltage levels through a free space by a digital communication system. So how can it possible, we'll see. Okay, so Now this is 2 level and this is M level. Therefore here this is M array PSK, because advanced version of this is M array, then that extension is PSK, that is M array PSK, where this M is total number of symbols. Now where M is total number of symbols, but where M which is always 2 power n, M is the total number of symbols, where n is, the array is M equal to power n, where n is number of bits per symbol, where M is number of bits per symbol. If M equal to 2 power 1, only 1 bit per symbol. M equal to 4, 2 power 2, 2 bits per symbol, like this. Number of bits per symbol. Number of bits generated per second is called as bit rate. Number of bits generated per second is called as bit rate, RB. Now similarly, number of symbols generated per second is called as symbol rate, or called as baud rate. How many number of symbols generated per second is called as symbol rate or baud rate? Note down. Clear or not? So now we'll see the M array signaling, which is nothing but M array PSK. Now this is M array signaling, which is nothing but M array PSK. Now here I am explaining 4 array PSK. Means, what is capital M? Capital M is 4, means how many symbols? 4 symbols. Okay. Now see here. Now M equal to 4. M equal to 4 means total how many symbols? 4 symbols. X1, X2, X3, X4. If M equal to 4, so M equal to 2 power n. What is the meaning of that? 4, which is equal to 2 power 2. Therefore, what is the meaning of this? N equal to 2. If n equal to 2 means 2 bits per each symbol. Therefore, now symbols are 4, but each symbol how many bits? 2 bits. Each symbol 2 bits. Okay. So M equal to 4, 4 symbols, and each symbol is allocated 2 bits. Therefore, so now the transmission of this level, transmission of this symbol, transmission of this symbol, transmission of 4 symbols. Okay. Now first we will see one symbol. Now this is, I'll just take X3 for easy calculations. Now 1, 1. Encoder output, right? This is the encoder output. which is what is encoder output? Digital data, binary data. Now this is the product modulator 1. Now this is the carrier sine 2 pi FCT. 90 degrees phase shifter. Product modulator 2. Now therefore, now this is PSK signaling. PSK signaling means the binary data represented in, now this binary data is represented in non-return to 0 for binary 1 plus voltage, for binary 0 minus voltage. Because PSK signal means the binary data must and should represented in non-return to 0 signaling scheme. So now let us check here. Now these two are connected to a adder circuit. Now similarly quadrature carrier multiplexing or not. So this is binary 1 is nothing but plus 1 volt into cos 2 pi, sine 2 pi FCT. Now this is again binary 1, which is nothing but plus 1 volt into cos 2 pi FCT. Therefore, now plus 1 volt into cos 2 pi FCT plus 1 volt into sine 2 pi FCT. This is the quadrature carrier multiplexing. This is the multiplexed signal. See here, two message signals but with the same carrier. Same concept. Two message signals. This is binary 1 or M1, M2 like that. Two message signals but with the same carrier frequency without interfere with each other. Therefore, this is quadrature carrier multiplexing. Carriers are orthogonal to each other. So now I want to calculate the phase produced by this. Let us take this is phase. What is the phase? If you want to find the phase, then represent it in terms of magnitude, square root of A square plus B square sine of 2 pi FCT plus phi, where phi is tan inverse A by B 2 pi FCT plus this is A cos 2 pi FCT plus B sine 2 pi FCT. Therefore, which is equal to tan inverse B by A. Tan inverse B by A. Then what happens? Square root of 2 sine of 2 pi FCT plus tan inverse B by A, 1 by 1, tan inverse 1, which is 45 degrees. Therefore, the phase produced by the symbol X3, which is phase which is equal to 45 degrees. Right? Now similarly, can we find the phases for the remaining? This is the general quadrature carrier multiplexing, or without that also you can easily find in a shortcut method. What is the shortcut method? Plus 1 volt, this is plus 1 volt, again plus 1 volt, this is plus 1 volt. Now what is the intersection point? This is the intersection. Put a dot, this is the symbol. Now this is the symbol X3. Now from the origin, from the distance from the origin to the symbol, the distance from the origin to the symbol is called as magnitude. The distance from the origin to symbol is called as magnitude. and the phase produced by this particular symbol, which is equal to 45, exact middle 45 degrees. In the same manner you can find all the remaining symbols phases also. Therefore now see here, I'll write directly, okay, without doing all these things. Now first x1 symbol, what is x1 symbol? 0 0. Therefore 0 means minus 1 volt. Again 0, minus 1 volt. x1 0 0. Minus 1 volt, minus 1 volt, 0 0. Now this is negative voltage, this is negative voltage. Now the distance from origin to symbol, the distance from the origin to symbol is called as magnitude. What is the magnitude? Now what is the phase? You can take it a positive phase, 0 degrees, plus 90 degrees, plus 180 degrees, plus 270 degrees. Now exactly the middle one is 270, 180, middle one. Therefore the phase which is produced here is 225 degrees. Therefore the first symbol is produced a phase of 225 degrees. Now similarly x2 0 minus 1 volt, minus 1 volt, and 1 plus 1 volt. This is minus 1 volt, this is plus 1 volt. The distance from origin to symbol, the distance from origin to that particular symbol is called as magnitude. This is the second symbol. Now the magnitude is as usual √2. Now this is 0. This is exactly 90 degrees. This is 180 degrees. Now exactly this is middle. Therefore this is the phase which is 135 degrees. Is it right or no? Now x1, x2, x3, x4. What is x4? 1 0. Now 1 means plus 1 volt, 0 means minus 1 volt. Now this is the symbol x4, which is 1 comma 0. The distance from the origin to the symbol is called as magnitude, and magnitude is √2. And this is the phase produced by this symbol is, this is 270 degrees, this is 360 degrees. Therefore exactly this middle, which is equal to 225 degrees. So these are the phases, 270, 360. This is nothing but 315 degrees, or you may say this is 0 degrees and this is minus 90 degrees. Exactly middle is minus 45 degrees. Yeah. Whatever you want you can. So therefore can you find all the phases for this? Now this is the phase which is minus 45 degrees, and this is the phase which is 135 degrees. Now can you check once here? Can you please check here? Now this is the symbol 1 phase, symbol 2 phase. What is the phase difference? 90 degrees. Symbol 2 to symbol 3, phase difference is 90 degrees. Symbol 3 to symbol 4, phase difference is 90 degrees. The phase difference between each symbol the successive phase difference between the symbol is 90 degrees quadrature. Therefore, this is called as quadrature phase shift keying. This is called as quadrature phase shift keying because the phase difference between the symbols are 90 degrees, which is quadrature, or you can say here the carrier frequency is same but both are quadrature in phase, both are orthogonal to each other. Therefore, this is also called as orthogonal frequency division multiplexing or quadrature carrier multiplexing, orthogonal frequency division multiplexing, quadrature carrier frequency multiplexing, all are same. Okay, so these are the symbols produced by the phases. So first you note down this. So this is nothing but this is MRA PSK, 4 array PSK. This is none other than QPSK, quadrature phase shift keying. Now all these things are we represented in a single diagram. Now this is the first symbol. Where is the first symbol? X1. This is the first symbol. Where is the second symbol? This is the second symbol. X2. This is the third symbol. This is the fourth symbol. If you observe, the phase difference between the symbols, see here, symbol 1 to symbol 2, symbol 2 to symbol 3, symbol 3 to symbol 4. What is the phase difference? The phase difference is 90 degrees. The phase difference between the symbols are 90 degrees. That's why this is called as quadrature phase shift keying. And the distance from origin to that particular symbol is called as magnitude. Now this diagram is called as constellation diagram. This is called as constellation diagram, and this is also called as signal space diagram. This is the constellation diagram or signal space diagrams. These are used for calculations of error probability. Probability of error calculation is possible with the constellation diagrams also. Now we'll see M array PSK. Now I'll take M array PSK. Okay. Now I will give one table which is very useful for us. Now this is M array PSK. Now here, now let us take this is M, where M equal to 2 means two symbols, S1, S2. Now N, number of bits per symbol, because array is m equal to, what is array? M equal to 2 power n. Therefore, m equal to 2, n equal to 1. Therefore, if n equal to 1 means only 1 bits per symbol, either binary 1 or binary 0. Okay. This is 1 bit per each symbol. 2 discrete voltage levels I want to transmit, but each discrete voltage level is converted to only 1 bit. Therefore, this is the phase difference between the symbols, which is 360 degrees by m, capital M. This is the phase difference between the symbols. The phase difference between the symbols 360 degrees by capital M. The phase difference between the symbols. The phase difference between the symbols, which is 360 degrees by capital M, which is nothing but 360 degrees by M is 2, which is 180 degrees. Which is 180 degrees. Then you go and check your phase difference between the two symbols. Now phase shift is 180 degrees. Then M array scheme is, M array name is, so M equal to 2, therefore this is called as 2 array PSK. This is called as binary PSK. This is actually what the PSK which we are already completed. Okay. So if you want a cancellation diagram, write that one also. The cancellation diagrams are very easy. Either binary 1 means plus 1 volt. Binary 0 means minus 1 volt, because this is PSK means non-return to 0. Then see here, this is the symbol. This is the symbol. The distance from the symbol to dot is called as magnitude. Now you see, what is the phase difference between these two symbols? This is symbol x1, this is symbol s2. What is the phase difference between these two symbols? Are 180 degrees. How much you are getting in your binary PSK class? You just go through it. The same answers you are already getting. Okay. So this is the binary PSK, which is matching or not? Yes. Now bit rate. What is bit rate? The number of bits generated per second is called as bit rate, or B, bits per second. Number of bits generated per second, bit rate. Now baud rate. The baud rate, which is equal to bit rate by n. Baud rate, which is equal to bit rate by n. Bit rate is RB, n is 1. Therefore, in BPSK, bit rate, baud rate both are same. Why? Because one symbol, one bit. So symbol rate, bit rate same are same. Symbol rate means baud rate. Bit rate means number of bits generated per second. Both are same. Baud rate, bit rate, bandwidth is equal to twice of the baud rate. Bandwidth, which is equal to twice of the baud rate. Now, what is the twice of the baud rate? Now, twice of the baud rate is RB. So, bandwidth equal to RB. You go and check. Now, we already see the Fourier transform analysis of BPSK. You will get the same bandwidth or not. Yes. Now, bandwidth efficiency. Bandwidth efficiency. The bandwidth efficiency is the bandwidth efficiency, which is nothing but the bandwidth efficiency, which is bit rate by bandwidth. The bandwidth efficiency, which is nothing but bit rate by bandwidth. What is bit rate? RB. What is bandwidth? 2RB. Therefore, what is the bandwidth efficiency? The bandwidth efficiency, which is equal to 1 by 2, 0.5, which is equal to 50%. Now, this is the array you can find for any number of discrete voltage levels or any number of symbols, you can easily get the answers. See the answers, how it is very easy for you. When m equal to 4, when m equal to 4 means 4 symbols, x1, x2, x3, x4. If m equal to 4, n equal to 2, which means 2 bits per each symbol. 2 bits per each symbol. Now, if n equal to 2, what is the phase difference? 360 degrees by 4, 90 degrees. When phase is 90 degrees, array is 4. Therefore, this is called as 4 array PSK. 4 array PSK and phase difference is 90 degrees. This is called as QPSK, a constellation diagram which we already have. Now, the number of bits generated per second is called as bitrate RB, and baud rate equal to bitrate by n, where n equal to 2, and bandwidth equal to twice of the baud rate, 2 to cancel RB. Therefore, in delta modulation, in QPSK, bitrate, bandwidth both are same. In BPSK, bitrate, baud rate both are same. Now, what is the bandwidth efficiency? Bitrate by bandwidth is a bandwidth efficiency. Now here bitrate and bandwidth both are same, so bandwidth efficiency is 100%. Now, if m equal to 8, so how many symbols? 8 symbols, x1, x2, x3, x4, x5, x6, x7, x8. So, if m equal to 8, n equal to 3, therefore 3 bits per each symbol. So, the phase difference between the symbols are 45 degrees. Now, if m equal to 8 array PSK, or this is nothing but 8 PSK. Bitrate is RB, baud rate is bitrate by n, bandwidth is twice of the baud rate. Bandwidth efficiency is bitrate by bandwidth 3 by 2, 1.5, which is 150%. So what you can understand here, if you observe here, as m increases, as array increases, what are the advantages you are gaining? As array increases, what about the bitrate? What about the bandwidth? 2RB. So as m increases, bandwidth is decreases. As bandwidth is decreases, obviously the bandwidth efficiency is increases. These are the advantages or not? The modulated signal bandwidth should be as minimum as possible. This is a very, very good advantage. But one disadvantage, as array increases, the angular separation between the symbols are decreases and the number of bits per symbols are increases. As m increases, n increases. As array increases, number of bits per symbol is increases. As n increases, more bits means probability of error is also more. Probability of error is also high. Probability of error is also high. Is it right or not? As n increases, more bits and error probability is also increases. This is somewhat disadvantage. But anyway, as array increases, the bandwidth is decreases, which is a very good advantage for us, no doubt. N number of objective questions from here. Okay. Now we'll solve classroom workbook in M array signaling problems. What is question number 1? Question number 1 is rectangular pulses are used for binary transmission to generate PSK signal whose pulse width is a rectangular pulse whose pulse width is given. Rectangular pulses are used to transmission of binary data to generate a PSK signal whose pulse width is given as 0.1 millisecond. Whose pulse width is given as 0.1 millisecond. And what he is asking is where B1 is bandwidth of BPSK, where B1 is a bandwidth of BPSK, where B2 is a bandwidth of QPSK, then what is B1 and B2 values? This is the question. Once again I repeat. Rectangular pulses are used for generating PSK signal, and a rectangular pulse whose pulse width is given to generate BPSK and QPSK. BPSK bandwidth is B1, QPSK bandwidth is B2. What is B1 and what is B2? What is bandwidth B1? What is bandwidth B2? So just now we have BPSK. What is the bandwidth of BPSK? The bandwidth of BPSK is twice of bitrate RB, and bandwidth of QPSK, which is B2, which is equal to directly RB. So we don't know RB in the question, is not given. But what is given? Rectangular pulse width is TB. If a rectangular pulse width is TB, what is its Fourier transform? A sinc function. What is the Fourier transform of rectangular pulse? Sinc. What is the bandwidth of the rectangular pulse? The bandwidth of the rectangular pulse is inversely proportional to pulse width. This is 1 by TB. This is minus 1 by TB. Now this is 0.1 millisecond. 1 by 0.1, 10 kilohertz. This is minus 10 kilohertz. From here you can easily calculate what is here. What is the bandwidth? RB. What is RB? 1 by TB. Now what is 1 by TB? 1 by TB is nothing but RB. How much it is? 10 kilobits per second is the bit rate. This is RB. So once if you know RB, you can easily find 2 times of RB. Now 2 into 10 kilo, which is equal to 20 kilohertz, is a bandwidth of BPSK. Now B2, which is equal to only RB, therefore which is equal to 10 kilohertz, is the bandwidth of QPSK. Understand or not? No doubt.